OK. So hi, everyone. I'm David. I'm the architect for Proofpoint's information protection product. We build a service that provides security for data on various cloud providers, like Google Drive, S3, stuff like that. We detect information leaks and unauthorized access. And internally, pretty much, is just we bring in a bunch of data from different APIs from cloud providers, and we do a bunch of data processing, which means that we have something like 50 different services doing all kinds of application logic on the data we bring in. And they're spread across hundreds of different machines, and they need to scale at different speeds, and they have different bottlenecks, some in CPU, some I/O bound. So we do just lots of production workloads. And so when I came to Proofpoint about 6 months ago as the architect for this project, pretty much every engineer came up to me at some point and asked me this question. So when are we going to do containers? Like, I said, all right, well, optimistically, probably 6 months from now. Pessimistically, maybe a year. And they'd all be shocked, like, what? What are you talking about? I can do Docker run on my machine, right? I have my service, I wrapped it in a Docker file. I can just run it in production right now. Like, give me 10 seconds and the keys to the Amazon web servers, and I'll do Dockers right now. And I say, no, well, hang on. Have you considered how you're going to monitor this thing? I say, well, no. And how are you going to collect logs from your container? I don't know, we'll figure something out. And how are you going to scale it, right? And what are you going to build? And how are you going to update images? And there's like 50 different things. And they'd all look dejected, like I kicked their puppy or something. And everyone will end up being disappointed, right? Because we can't go to containers anytime soon. And so this is how this talk came about, really, which is like this conversation, which is, I'm guessing, very common in the industry, which is there exists a gap between using Docker or using containers on your machine and actually running stuff in the real world, in production, at large scale, right? And there's a bunch of things you need to consider. You don't necessarily have to do them, and a lot of them are DevOps-oriented. So I'm going to ignore the DevOps stuff, right? Because we're in a developer conference. I'm guessing most of you are developers. Raise hands. Who's a developer? Pretty much everybody, or no one willing to admit that they're DevOps. Anyway, so I'm going to skip the DevOps stuff because there's a bunch of dev stuff that needs to be done before we can go from writing a Docker file on your laptop to actually running a containerized service in production at high scale, stably, with updates and all the other stuff. Right, so this is what we're going to be talking about today, and all the lessons we learned in the 6 months it actually took to roll out the first container to production. So the first thing you do when you approach, by the way, let me ask you this. Who has used Docker? Pretty much everybody. Excellent. You can all go. No, I'm kidding. Please stay. Who works at a company that has containers in production, not testing, production? OK, a lot fewer hands there. There's like 20 hands out of 80, right? Who has a proper managed Kubernetes cluster in production? It's like one guy, two. OK, good. You're the right audience for this. So you're all sitting on this gap of, OK, well, I know what Docker is. I can use Docker. How do I run this in production? And so the first thing we're going to talk about is how you actually build containers, right? Because obviously, you can do Docker build. I'm trusting everybody here is very intelligent, and you can Google how to build a Docker container and discover how to do that. But there's a difference between doing that and actually having containers that are appropriate to run in production. So I'm going to show you just one thing as a first demo, because I like demos, and I think the first thing you need to do is show something useful. All right, so I'm guessing if so many people showed hands that they know how to use Docker, you can recognize a Docker file. All right, this is a Docker file for a very simple .NET Core application. All it does is run hello world. And as you can see, we use the .NET SDK base image. Right? I'm sure everyone's familiar with base images. When you write a Docker file, you can specify what Docker image is going to be built from. Right? In this case, it's the official Microsoft .NET 2.1 SDK, which lets me compile and build a .NET Core program. And all it does is copy my code over, run build on it, and then run the application. That's all it does. It's very straightforward. Obviously, we can build the image, right? So let's make it a bit bigger. Docker build. Just build the whole thing. It builds very quickly, because I've done this before. So let's do Docker images, grep full. Right, so we can see our image, right? And the first thing we notice is this image is almost 2 GB large because it's based on the .NET Core 2.1 SDK, which itself is almost 2 GB large. So if we start pushing these images in production with updates every now and then, first of all, we're going to have to store them in our repo, right, in some registry or whatever repo you set up, and that's a large image to push to production. And it takes a while to build and run, and it contains a whole bunch of stuff we don't actually need in order to run this application in production. Most of these 2 gigabytes is just the environment to build the application. So this is why Docker introduced phased builds a while ago, or multistage builds. And so the first thing we do is we just, let's colorize it. So is anyone familiar with multistage builds? Are you using it? Like a few people. All right. So this is a new thing. It's out about 6 months ago, Docker 11, I think, 17, I think. And so what you can do is you can specify different build images for the build stage and for the actual execution, right? And so basically, it will compile your application in one image and then copy the artifact that gets created, and it will run it in another image, which is hopefully much smaller. So there's only 2 lines that we added, right? So we say we still build it in this .NET 2.1 SDK, but then we say, OK, we'll take this other build base image, which is the .NET 2.0, 2.1 runtime, which doesn't include any of the build environment. We'll copy the output from the previous image into this image and save that. And this is the one we're going to use. And when we do this, all right, so right, we run this, and we build this image. It gets built just as quickly. And so now we do Docker images, grep multi, and we get an image that's 180 megabytes, exactly 1/10 the size of the previous image, which is much more manageable. And obviously, I picked .NET because it's a very extreme example. Like the base image is huge, but it works pretty much the same across most applications, right? Whether it's Golang or Java or Scala, whatever, you have a giant build tools image, and you have a much smaller runtime environment. So this is a thing that's very trivial to do, but you really need to do this. Obviously, this is something you do once and you forget about it. But it's important to actually pay attention to small things like this. And obviously, Docker files are code, just like any other code you need to maintain. Usually, you put them in the same source control as the actual application, and you deploy and you store them at the same time. So this is just the first thing, and I know it's a small thing, but I'm starting something light. Now, if you have 50 different services written in 3 different languages, as we do, it still takes a lot of work to actually go and wrap each one in a container, right? And you don't want to go and handcraft a Docker file for each one of them. You need to build some kind of tool chain which generates Docker files automatically, hopefully. And there's some stuff to be built around this, right? So this is just the first thing. Now that we have our build image and we have something we can run in production, the next question comes, OK, well, how do I run this, right? Obviously, doing it on my laptop is easier. I do Docker run, give it the name of the image, and it runs. If you want to do it in production, you have a few things to consider. First of all, is it going to be on virtual machines, or is it going to be on bare metal, right? We, at Proofpoint, we use Amazon for everything, so it's pretty much a no-brainer. We're going to be using Amazon for this as well. And then the question comes, OK, well, do we just run containers directly? So because we can do Docker run on the machine. Do we use some kind of orchestrator, specifically Docker Swarm or Kubernetes? Or do we spin up some kind of managed service? Pretty much every major platform today has some kind of managed container service. There's Amazon Elastic Containers. There's Google Cloud, managed Kubernetes, all kinds. All right, and so we sat down with our DevOps. We brainstormed. And the first line, right, the standalone containers, that was a legitimate option we considered because in our case, our main bottleneck is DevOps resources. We have a lot more developers than we do DevOps. And so we looked for things we can actually do quickly to get benefits from running containers without spending 6 months just doing DevOps works to spin up a managed instance of something. Ultimately, we discarded this idea, mostly because we were afraid to get locked into this suboptimal deployment, and we just enshrine something we were initially not happy about. And so we threw that idea away, and then it was a question of, OK, do we do Docker and Docker Swarm, or do we do Kubernetes? In this case, Kubernetes won pretty easily. It's much more complicated and complex, and it also, for that reason, it has a lot more options, which we actually like. It has things that address automatic scaling and better health monitoring than Docker Swarm. And it has stateful sets, which lets you run stateful applications much easier in containers, which I'll talk about in just a bit. So overall, it's much more complicated. There's a much higher learning curve to actually using Kubernetes, both for the developers and for actually deploying that as DevOps. And ultimately, the thing that actually cinched it for us in favor of Kubernetes is the only cloud provider which gives us managed Docker Swarm is Docker Cloud itself. And so there's a single provider, and we didn't want to get locked into that, whereas pretty much every major platform today has Kubernetes as a service. In fact, Amazon AWS came out with Kubernetes as a service just last week, on June 6th, I think, right, which is pretty new. So Azure had managed Kubernetes since last year, I think October last year or so. Google have had managed Kubernetes forever, pretty much. And so even though right now we're looking at actually deploying our own Kubernetes cluster, the goal is eventually to migrate to a managed Kubernetes cluster and save all the management overhead from running and monitoring our own cluster and give it to someone else and just pay for the service. That's one of the reasons, for example, we wouldn't go with Amazon Container Service. If anyone played with Amazon ECS, it's built on top of CloudFormation deployment scripts, which is like its own different language, which has nothing to do with either Docker or Kubernetes. And if we build and automate all this infrastructure around Amazon Container Services, and we want to go to Kubernetes eventually, we're going to have to rewrite the whole thing from scratch. Whereas if you just deploy Kubernetes over our own right now, build all the automations around that, if we move to a managed Kubernetes instance, it's just going to save some management overhead. We won't actually have to rewrite all of our dev deployment toolchain at all. So that's pretty much the part that actually sold it for us, even though it has the highest initial cost of setting it up. Right? So actually, deploying Kubernetes is a large job, mostly DevOps related. Once you have that, then you can start talking about all the other things on the dev side of how you actually run stuff on Kubernetes. So let's take a look. In general, there's 3 ways to run things on Kubernetes. One, you can just use commands directly, right? You can go and you can do Kubernetes run, same as you would do with Docker, and give it the name of the container, and it will actually run. So for those who aren't familiar, when you run Kubernetes, you have your Kubernetes cluster. By the way, on my laptop, I'm using Minikube. If you want to play around with Kubernetes, I strongly recommend you download and install Minikube. It's very, very interesting to just play around with. And then you use the command line tool called kubectl, which is like the command line interface to talk to your Kubernetes instance. And you can do all the normal stuff like kubectl, get pods. We don't have any yet, but we'll build some in just a moment. And so you can submit commands directly to the cluster. That's actually not very sustainable if you want to look at automation and DevOps tooling. So the second thing everyone looks at is actually writing deployment files, usually as YAML file or JSON files. And the deployment file describes what you want to deploy. This is very similar to Docker. In Docker, there's a file format called Docker Compose files, and you describe all of your services in that. So let's take a look at one example of how you would do that. I have a very silly Node.js application, which just does hello world. We don't care about the application. We just want to look at how you deploy that. Right, so we create a YAML file called deployment.yaml. There's a format. There's several different files for Kubernetes. One for pods, which are collections of containers. Deployment is a higher level abstraction. It can have multiple pods, so multiple services talking to each other in the single deployment. And above that, we have a service which exposes parts of your deployment to an external endpoint. So it gives it an external API and a load balancer on top of it, and you can actually access the deployment from outside the cluster. So here we're going to deploy whatever it's called node app, right? And here we can specify how exactly we're going to deploy this. So we can specify replicas. We're going to run one replica for now, and we'll change it later. What are we going to run? We're going to run an image called node app 1.0. This is actually in our Docker repository right now, exposing port 6060. And then we can specify a bunch of stuff, which you can do both in Kubernetes and in Docker. It's just more advanced in Docker, in Kubernetes. You can specify the CPU limits. This is in millicores. So 1,000 millicores is 1 core. So this will actually be using 1/10 of 1 CPU core and 64 megabytes of RAM. This is the maximum amount of resources it can use. This is what it requests initially, so I can actually give it less. You can use, I don't know, 32 megabytes of RAM initially, and then if it requests more, it can go up to 64. We can specify things like health checks. This is one of the things I actually like in Kubernetes. You can specify health checks as a REST endpoint. You can't do that in Docker. Docker actually runs a command in the container itself to do health checks, which is kind of annoying, and I'm not sure what to do about that. Because if you have a REST endpoint on all of your services, for example, we used to run all our services on VMs, and all of them had a health check REST endpoint, which we just probe normally. So migrating to Kubernetes is very natural because it just does the same thing. It goes to the health check endpoint and probes it. For Docker, we had to do something weird like running curl at the endpoint and looking at the exit code for curl. And that also means you have to package curl in your base image, which, for example, in the .NET example, there's no curl in the base image. So we'd have to bake the tools to do the health checks into every production image, which is cumbersome and just not very pleasant to work with. So this is a thing we like in Kubernetes a lot. So we specify this. This is the health endpoint. It will get called every 30 seconds. And the readiness check, which is different, this just specifies when the container is actually ready. And this is when Kubernetes considers the container to be running. Until then, it's in a sort of unready state. Right? And we can specify a bunch of other stuff, things like mounting disks and more with networking and services and stuff. And so when we run this, it will spin up one container, and we'll run our node app. Right? Of course, that's not enough, because it will spin up the container and only expose it internally within the cluster. If you want to actually have the endpoint accessible outside the cluster, we have to also specify a service, build a service on top of it. Service is much easier. It's another YAML file, kind service. It says, OK, well, you take node app, you look at port 6060, and you expose it through a load balancer. So however many containers we end up with this label, node app, they'll all be exposed with one load balancer. And we can talk to the load balancer. It will round robin through all the containers. Right, and so from here on, the deployment itself is quite easy. Apply deployment YAML. This goes and creates a new container, and then we can create a service. Right, and so we can now look and see if we have any containers running. So get pods. We see that we do have one pod running. You can see that it's not in ready state yet. It takes about 15 seconds for the initial ready check to actually be completed. So eventually this will, there we go, it is now ready. If we had multiple different types of containers in our deployment, and we could specify that one of them needs the other to be ready before it spins up. For example, if I have a set of microservices, which pretty much everyone has these days, one service needs another service to actually be available before it can come up. Trivial example, we have a config service. It's a REST service that exposes application configurations to all the other applications, and an authentication service, which other services use to generate auth tokens. So both of those need to actually be up and available before any other service can actually come up. Otherwise, it will come up, try to get the identity, fail, and crash again. Right? And so this is very convenient. We can specify how and in which order each one comes in. This is also very useful when you do rolling upgrades. So you can't, let's say you have 10 instances of the same service, you won't decommission too many of those before new ones become ready. So you won't have an outage at any point during the rolling upgrade. OK, so we have a service. We can actually access it. Service node app. This just tells Minikube to open it in a browser. As you can see, yes, we have. It is exposed on this particular port, and it just says, hello world. It's not a very interesting service, I'll admit. But it works. Okay, so we can do all kinds of exploring. We can do describe on the service node app. We can get all kinds of information from it, the internal port, the IP, all that. And so this is very, very useful. And at this point, we have enough to work with that we can start defining automation around this, right? So we can have the deployment YAML and the service YAML as part of our code, same as the Docker file, which builds the actual container. If the deployment refers to multiple services, it makes sense to have it sit outside the actual service in a different repo, which just talks about deployments. It's a little cumbersome to manage, right? When you go and you change one service, maybe add a port or change something about it, you have to go and remember to go and update the deployment, which is in a different repo in Git. It's just a process thing. You have to get used to it, pretty much, because it makes more sense to separate the deployment files. It's more of a DevOps job. This is, by the way, a question that I get a lot. Where does the line cross between what's a dev job and what's a DevOps job, right? So we can actually pretty much we can specify a few things which are clearly dev or DevOps, right? So writing the code, writing the Docker file, clearly a developer job, because you're the one who knows what the service exposes, how it works, all that stuff, right? Writing automation around actually running containers, right? So running the deployment YAML file, calling kubectl, clearly a DevOps job, right? Because that's what they do, managing the container, all that stuff. Somewhere in the middle, there's stuff like building the deployment, right? And specifying the hardware requirements for the service. So this is something that probably you will need to have some process where dev and DevOps have to work together and specify, okay, so we know how the service we wrote behaves. It needs this much memory and this much CPU. And the DevOps will come in and say, okay, well, our machines have this many cores in each one of them. Let's change the granularity of how we specify resources. This is something that will have to be collaborative. It really helps to have your dev and DevOps in close communications, at least, if not physically in the same location. In our case, we actually have the dev and DevOps sitting together, mixed, so they can throw stuff at each other. If things break, which they do. All right. So that's pretty much the short how do you do stuff with Kubernetes. There's one extra thing. There's a tool called Helm for Kubernetes. It's how many people use any kind of package manager? So NPM, let's say Brew for macOS, right, or Chocolate for Windows. Right, it's a package manager where you go, Chocolate install wherever 7-zip, and it goes and downloads a package, installs 7-zip for you, right? Or same thing with NPM. So there's a tool similar to that for Kubernetes packages. It's called Helm. It has a server component called Tiller, which runs in your Kubernetes cluster. And so you can use Helm to submit deployment packages to Tiller. And internally, Tiller will go and run all the kubectl commands for you. It will actually talk to Kubernetes for you and execute all the deployment. It will download images, set up stuff. It just saves you a lot of work. And so deploying something becomes just a single line of Helm install something, right? In our case, there's a large library of pre-built Helm packages, or you can build your own Helm package. And so instead of having a bunch of deployment YAML and service YAML files scattered around, you'll have your own single repository of just charts for your Helm. And the deployment becomes, OK, I submit changes to the package, and then the automation calls Helm install this new package, service 1.0. Right? It works something like this. So let's say, right. No? Pretty sure we had WordPress or something. Oh, yeah. Update. You know what? We're not going to do this in the middle of a talk. You can just trust me that it will install WordPress, and it'll be wonderful. We can all blog about this experience together. And then we can delete it with Helm deletes, whatever, right? So pretty much the whole point is this is like the highest level of abstraction you can have for deploying stuff in Kubernetes, where you don't even specify deployments, all the deployments parameters. You hide them within this Helm package. It's very convenient. We feel it's mostly overkill for us. We don't use it right now because it takes more work to actually write Helm packages than it does to generate deployment YAML files, which we just do with a script. At some point in the future, if we have more services running in Kubernetes, we will probably go to Helm. For now, it's not very useful for us. We had a talk with Jonas over there yesterday about that, and he mentioned one really good use case we didn't think of, which is if you have a lot of customers and you want to spin up a dedicated instance of something for every one of your tenants, of your customers, it is actually very convenient to just wrap whatever environment you want to spin up as a Helm chart, and then you can go and do Helm install this for every customer, and it automates it very easily, which is pretty cool. Not useful for us, but just a cool idea in general. All right, so the counterpart to Kubernetes deployment scripts in Docker would be a Docker Swarm, which is the actual orchestrator for Docker, which takes care of scheduling containers and running stuff. And Docker Swarm uses deployment files called Docker Compose files. So we can take a look at one Docker Compose file just for comparison. It's mostly similar. A Compose file looks like this. You see that it's actually conceptually very similar to what we had with Kubernetes deployment. We have the image, right, that we're going to run. We have the deployment parameters. Let's say we're on three instances of that. We can specify the restart policy for the service. If we want to do something, we can specify, I didn't do it here, but hardware limits. And we can specify other services it will depend on. And so, for example, we have two services here, a service called Web and a service called Redis. And so Web will be able to access Redis with the DNS name Redis. Right? This also automatically creates DNS routing for every service, so they can actually see each other and talk to each other. This replaces whatever complex service discovery mechanism you might have. Or maybe not. Maybe in some cases it makes sense to actually use an external service discovery mechanism. We still run with Zookeeper and Vault in our case. So this works pretty much the same way, right? And you go and you do Docker stack deploy. Let's just try one. You know what? We'll actually do a different example to make it interesting. One last thing to talk about is managed services. Right now, there's a reason we didn't go to managed Kubernetes on Amazon. It came out last week. It's not even available in the data center where we're running our stuff. It's only available in North Virginia and I think Ireland. Our stuff isn't in either one of the data centers, so we can't use it. Also, it's 1 week old, right? It's 1 week out of beta, so we're going to give it some time before we put all of our production infrastructure on that. If you're in Azure, so the Azure managed Kubernetes has been around for almost a year. At this point, I'd be more inclined to trust it. I'd actually consider doing a POC on that if we were actually running on Azure, which, as I said, we aren't. And if you're in Google Cloud, you're in luck. That's actually the most trustworthy and battle-tested managed Kubernetes deployment you can get. So you can give it a try. Tell me about it if you want. So let's talk about the next thing, right? There's a bunch of stuff once we have our containers running, right, there's a bunch of stuff we need to take care of, which doesn't work quite the same when you have a lot of containers working in a bunch of anonymous instances or pods instead of just named VMs, right? And the first thing that happens is logging changes, right? So normally, the way people do logging in production these days is you have some kind of log shipper. If you're using the Elasticsearch Elk stack, right, so you'll have Logstash or FileBeats or something running on every instance, and they will get your log files and then ship them somewhere else. If you're using Splunk, you have the Splunk agents shipping logs to the Splunk indexer. And it pretty much works all the same way, right? If you're using a service like, I don't know, Logs.io, something online, they give you a log shipper, which takes all of your logs, pushes it to them. Right? And this works nicely if you have a bunch of VMs running your workloads. Because VMs are named, they don't disappear very quickly. Even though technically you can restart VMs, in practice, I checked. On average, we restart every one of our VMs less than 1 time a month. Right? So we can actually trust the VM to stay up for quite a while. And the names of the VMs don't actually change, right? If we have a VM called Web Server 3, it's going to restart and come back as Web Server 3. That's not the same way it works with containers, right? A container, first of all, can get rescheduled willy-nilly. So Kubernetes can just decide it needs to move some resources around. It will just kill a container, spin it back up on some other node. And then the container name is going to be a random GUID, so you can't trust the name of the container to remain the same, right? And so in your application, the first thing that needs to be changed is how you actually treat logging if you want to go and look for things that you've logged, to diagnose problems, right? Let's say there's an issue which happens once every 1 million operations, and you want to find out if it's related to a specific machine or a specific image version. So you need a way to actually go and track the image, the Docker container, which actually changed names several times, right? Maybe it came down, it came up again, came down, came up again, and the name of the machine itself changed a bunch of times. But you need to have a way to actually connect all these logs together, right? And so you have to consider how you're actually going to mark your log messages to make them available both on the application level. Let's say we have 50 services, so each service has to identify itself, so you can find the particular service logs, and the container itself, right? So you have to actually mark somehow which container is that's sending the log. And so you'll be able to diagnose whether the message is, for example, the problem is systemic, right? It's on all containers, or if it's related to one particular container, right? And so the next thing you think of is where does the log shipper sit, right? So one of the things we had when I came to Proofpoint is we log a lot of things, right? So we do a lot of data processing. We process hundreds of millions of messages, and for every event we process, we actually log something like, on average, 12 different messages into the log. So our log database is actually growing faster than our actual database. And so the first thing we did was we stopped parsing logs. Instead of actually writing logs to disk and then having Logstash, in our case, we use Elk. So Logstash read them from disk and parse them. We spun up Logstashes on every instance, and so the application sends logs to Logstash directly through TCP. This lowered the CPU usage by more than 50%. We were spending actually more CPU parsing logs than doing the real business work we were actually meant to do. And so the first thing, we got rid of actually reading log files. When you move to containers, it's actually not trivial to get rid of reading log files, because the default way all container orchestrators work is you write to std out. The instance collects all the logs. So for example, Docker collects all the logs that get outputted from the container, and then it's exposed through Docker logs. You can go and do Kubernetes logs or Docker logs, and it brings you the logs. When you have enough logs, that becomes completely impractical, because this takes longer than the actual job the container is doing. So that had to go, and we deployed log shippers that our applications talk to through the network. And so here is the question, do you put the log shippers inside every container? And the benefit of that, of course, is the log shipper is local to the application. All the application has to do is send logs to localhost whatever, 5,000, and it will always find something listening for logs there. The problem with that is we have to add Logstash to every container. We have hundreds of containers, right? So you multiply however resources Logstash needs by the number of containers we have, that becomes a lot of resources, right? Because Logstash is a Java program, it's pretty fat. So that's probably not the best idea. The second thing that we considered would be putting Logstash on every host, right? Instead of putting it in every container, you put it in every host, which hosts, let's say 10 Docker images, 10 containers. And so it's still kind of local to the image. There's no network traffic involved because it talks to the local loopback interface. But that would mean that we can't go to a managed Kubernetes deployment anytime soon. Because when you're using a managed service, you don't actually have access to what's running on the host. You only have containers and everything outside the cluster. So you can't put log shippers, and this is going to be the same thing when we talk about metrics in just a second. You can't put any kind of receiver on the host itself. So the last option, obviously, is to have your log collector or stats collector outside your container, right? Which means either it's a container of itself, so you spin the log shipper as another container in the cluster, or you just have it completely separate. It's just a VM running somewhere else that the cluster can see. Right? The benefit of having it in the container, obviously, it's very nice. You can manage it the same way you do all the other containers. Unfortunately, it can go down anytime, right? You need to actually now take care of it. There is network traffic involved. Maybe you're sending logs, and there's a network disruption. So now you lose logs on the way to the log shipper, right? Same thing with metrics. It's less of a problem with metrics because they're mostly statistics-based. But with logs, we really don't want to lose any logs. So in our case, we're still deploying log shippers on the host itself. If and when we go to managed Kubernetes, we will have to resync this because it's not going to be possible to do that on the host. And so let's take a small example of how you actually can do logging. I have a small logger application here. So let's just look at the code for just a sec before we do that. This is a logger. It's a very small Node.js application. Why Node.js? I just figured I'll mix things up. We'll have some .NET, some Node.js. Be glad I didn't write in F#. So in Logstash, it's very easy to talk to Logstash from Node.js. You just tell it which host it is. It's DNS name Logstash, port 5000, and then you just send logs into it, right? So it just sends a message when the application comes up, and every time I go to a REST endpoint, it says, OK, so we called the endpoints, right? So it's very trivial logging. And there's some interesting things I want to show you that we can see in the logs, right? So we'll spin up a bunch of these, right? Let's go and spin up a few of the logger applications. That's our Docker file and our compose. We can actually spin up a few of those. Let's actually have more than one running. It doesn't matter. So this is written in Docker Compose, just so I can show both Kubernetes deployment and Docker Compose. So the way to run it is docker stack deploy this file, and we'll call it logger. Sorry, it's -c, actually, to use to Kubernetes. All right, so now it's created a service, same thing as kubectl deploy does. It created a service called logger. We can look and see that it's there, Docker stack ls. You can see that now we have a service called logger running. It has one container. We can scale it. We can go Docker service scale logger equals 3. Did I not name it right or something? Oh, it's called logger. Logger, sorry. Equals 3. And now we'll have 2 more of those. And we'll be able to just call it whenever we want. It's exposed on port 8080. OK, so curl localhost 8080. Right, and obviously we get hello world. Wonderful. Each one of these will probably log something. As it happens, I have elk running right here. And we can go, we can see all of our logs. As you can see, we had one log saying, let's make it bigger so you can actually see it. So the first message was the service coming up. The next 2 messages is 2 extra containers spinning up, and each one of them says, OK, I came up. And the thing you can see here is each one of them has a different host name, right? This is the first one because I deployed it to a service, and they get assigned random host names. So you can't actually trust them because each container is a different host name. And so every time I called them, as you can see, we have a load balancer. So every one of my curl commands actually hit a different container. And each one of them logged something else. And so here we can actually look at 2 things. One, each one has a label. I specify in the application the label. So I do have something central connecting all these log messages to my logger application. So if I parse this a bit smarter, because I was too lazy to actually go and configure Logstash, this would be a separate field, and I'd be able to filter by the label itself, by the application label. So I could go and find all the log messages belonging to the application logger from all the containers. Whether containers go up or down, it doesn't matter. Or I could go and I could sort or filter by the actual container name. So we can go and you find just this container. So I only want messages from this host. And so now we only have the 2 messages from this particular container. So I can go and I trace problems that occurred within this specific container and not any of the other copies. All right? And so this is something that we didn't actually have to address at all when we were running VMs. It's a thing that you actually have to consider how you're going to be looking for logs from your containers. Okay, this works more or less the same for metrics. So if we go and we look at monitoring, right? There's a few things you can monitor. By the way, everyone clear on the difference between logging and monitoring, right? Logging is writing log messages with the internal state of the application somewhere. And monitoring is runtime monitoring, so you send some kind of metrics for logical operations that the application does, and for things like CPU usage, disk usage, how many requests and how long each request took, things that are actually statistical in nature. And you can go and build pretty graphs on top of them. So for monitoring, there's also a few common tools in the industry. Does anyone use StatsD or CollectD in their application? There's like 2 people. All right. Well, there's a few others. Datadog. Anyone who's running Datadog? OK, a few. So that's an online service which provides monitoring and metrics collection. And there's a few others. And generally, it works the same thing as with the logs. You have some kind of log collector. Usually, they use UDP, because in the case of logs, you don't really need reliable delivery. You just need it to be very fast and very cheap. So StatsD is an open source project from Etsy, which it's a UDP service which collects a bunch of UDP packets as metrics, aggregates them in memory, and then writes them all at once to some kind of metric storage. Could be Elasticsearch, for example, and you run Grafana with graphs on top of it. Could be InfluxDB or any kind of time series database. There's a bunch of them. There's CollectD as well. And here we have the same question of, first of all, do we run the metrics shipper on the container, on the host, or completely externally? In this case, it's much easier to decide to run it externally because, as I said, we don't really care about losing single metrics. We care about trends, usually with metrics. So in our case, we can just spin up the log collector as another container, expose it as a service, and everyone can run to that, write to that very easily, which is what I'm going to do in the demo here in just a sec. And so the second thing is, the most important thing is, how do you collect metrics, right? Do you collect metrics at the application level and ignore the fact that they could be coming from different containers? Do you collect metrics at the container level, but then you would need to aggregate stuff coming from all the containers into one application? Or do you do both, right? So for different use cases. And the answer is different things make different sense in different contexts. So for example, let's look at one small example of how you would actually collect metrics. Right here. So let's take a look at the metrics application, a very straightforward .NET application, web API. I hope, can everyone read C#? Who can read C#? It's like almost everybody. OK, good enough. OK, so we have a very, very silly REST API, right? We have get, and we have get by ID. That's all it is. That's pretty much 95% of all applications, by the way, in anywhere. All you do is just get stuff or get stuff by ID. So here, it makes sense to collect a few things, right? I want to record for how many get commands were handled. I might also be interested in how many get commands are handled by every container instance. The reason for counting all of them at once would be because I want to know how many gets I actually handle in my application. So I want a graph that says, OK, do you have this many gets per second at any given moment? And if I see the graph dip, I can say, OK, well, something wrong happened. I also want to see how many requests every container serves, because maybe it makes sense to monitor and see if one particular container is underserved or overserved. Maybe I have problems with routing or load balancing or something. And so it makes sense to actually also collect gets metrics by container. In this case, the way I'm choosing to select containers is just look at the machine name. The machine name for a Docker container is just a GUID, right? It's always random. Now, there's a few problems with that. We'll deploy this in just a sec. I'll just talk about the second case first. In the second case, we're also passing the ID into the GET request. Now, here's where it gets tricky, because now I could collect metrics by ID as well. So I could do something like create a new metric called get.theID, and so I'd have a separate metric for every unique ID in my system, right? When you compound that with containers, I'd launch metrics called container name, or machine name in this case, .get.id, and so I'd get a separate metric for every ID for every container instance ever in my system. This can exponentially increase to a lot of different metrics. Metrics cost money. If you're using Datadog, they directly cost money. You pay per custom metric. If you're using any kind of local infrastructure like StatsD or Grafana or Graphite or whatever, each metric is usually a file on disk. For example, Graphite uses Whisper. It pre-allocates 80 megabytes for every metric. So even if you only send one data item into the metric, it still uses 80 megabytes of disk space. You take, let's say, 1,000 containers like we do, multiply it by however many containers actually come back up and down, multiply it by the number of unique IDs in the system, multiply it by 80 megabytes, very quickly we're looking at tens of terabytes of just metrics data, right? And so this becomes very expensive very quickly, and even though we might be interested in how many metrics of those we want, it is just sometimes not practical to log everything. The other side of it is, so you might ask, why are you logging both this get, and get by machine name? Can't you just log only this, the second one, by machine name, and just aggregate, sum all the metrics together? Yes, technically I can do that. But that actually also costs money, right? Because you aggregate at runtime when you read the metric. So if you build a graph which says, build me a graph by summing up all the machine name get metrics together, it will do that in memory at runtime every time you refresh the graph. For example, in the case of Grafana, it will go and it will query the data source every time. So every 5 seconds it refreshes. If you're looking at, let's say, 1 million different IDs, you'd query 1 million files and do this, the aggregation in memory. We crashed our Graphite service almost every day before we solved that. So this is a thing to consider. All right, so let's run this and see if that actually runs. We can go and do, let's go to our metrics. Stack, deploy, metrics. So this actually just runs that application we just saw as a service, and now it exposes it. Let's say Docker service ls, and we can see it. There we go. We have our metrics service on port 5050, and now we can spam it a bit, right? So we can do curl localhost 5050, and hopefully it will actually respond. It's a .NET application, .NET Core. It takes it a while to actually come up, and there we go, and do the just-in-time compiling. And I'm not sure. I think I gave it way too little CPU to actually do this. So as you can see, it responds every time with a hello world and the ID of the container where it came from. And every time I run this, it's a different container. Right, so now that we had 3 containers, they all got actually compiled. So now the responses are very quick. We can also go and get them, do a get by ID or something. And then we'll go and take a look at all the metrics that we collected. So here we can look at Grafana, which is actually what we use. And I prepared in advance a few different types of metrics. So this is the get count, right? This is how many get requests we actually sent. Right? We can also get the get count by ID. Right? I was only calling ID 1, but if I called a few of the other IDs, we'd get different graphs for every ID we requested. And you can see it gets progressively worse because we get more metrics. Right? We can go and look at get by container. You'll see that there are 4 containers. I only spun up 3. There's also my MacBook here because I was playing with it earlier. But this metric remains. The container is gone, but the metric remains. It's not going to go away until we do cleanup. So this is going to expand to however many containers there exist in our system or have ever existed within the retention period. Right, so this particular counter is going to get very complicated very quickly because containers tend to go up and down, up and down. Also, the worst part is, let's say I rescale our metric system. Right, so let's go here. We'll do Docker service scale metrics equals 5. Okay, so I spun up 2 more. Well, we'll have spun up in just a sec. Waiting for it to spin up, and now I'll scale it back down, right? So we configured auto-scaling. We want auto-scaling, so we're going to scale it back down to 2, right? And 3 containers just disappeared. And now I'll go and I'll run some metrics, and we'll see that we'll do curl localhost 50 something. As it happens, it killed 3 of the newer containers and kept the old ones. But it could just as easily have killed the new containers and killed the old containers and kept the new ones. And so what we would see here is the graphs would go up with metrics and then disappear because the container died. And there would be a new section of the graph starting and going up and then disappearing again, because every container would actually log its own metrics and then disappear and a new container would start. And there would be no continuity. And this is a graph that's actually very hard to use. And if we go over to this one, this is the one that actually logs get by ID and by container ID, which is the most cardinality we have. And this will become unreadable very quickly, right? So it will have as many containers and as many IDs as you have. And so it'll be very short, small graphs. As soon as the container dies, all of the graphs become unreadable. And so you'll probably never use this as is, unless you're specifically investigating a problem with a particular container ID, which hardly ever happens. So to sum this up, it makes sense to go over every metric in your application and evaluate every use case, whether you want to log it at the application level, because what you care is how many operations the whole application done, or if you want to log it by container. And if you will want to log it by container and then aggregate, it makes sense to just create a new metric. Even though you're paying for the new metric, it's still cheaper than aggregating all of the other metrics in memory every time you actually read them. All right? And so, as you saw earlier, there's one small addition to this, monitoring health. And so in Kubernetes, if you want to monitor health, you can either run a command in the container itself or call a REST endpoint, which is much easier. We strongly prefer using REST endpoints. And there's a couple of guidelines which I don't necessarily agree with from Kubernetes about health checks. They strongly recommend that health checks be very quick. I don't know if that's true, because usually what people do for health checks is just an empty endpoint, which returns OK. Presumably, if the service is down, the REST endpoint will not return OK. And that's how you determine that the container is healthy, which isn't really the case in real life. Because, for example, we have containers or applications that come up. They connect to 2 different databases and 1 Elasticsearch and Kafka and a bunch of other stuff. And so the health of this service isn't defined by the fact that the service is still up. It's defined by whether it can actually do its job, right? And determining whether the service can do its job means probing every database or every connection actually it relies on, or in our case, we actually do it in the background and store the last time we actually saw a healthy database or got a message from Kafka. And then the health check is whether we had a successful health check within the last 5 seconds, right? And if we haven't seen any messages from Kafka for 5 seconds, and we haven't used the database in 5 seconds, and as far as we're concerned, the service isn't healthy, right? And so this is something that actually bears thinking on, because you need to go to every service. If you have many services, you do need to evaluate each one and consider what defines health for this particular service, right? Is it just the process itself is up? Is that enough? Or is it because it actually can do all of its job, right? And how you define, is it the first time you failed to connect to the database, or is it several times you failed to connect to the database? This is actually pretty much similar to what you would hopefully do regardless of containers. But in the case of containers, it becomes much more important because, first of all, containers are much less reliable. They, in terms of they can go up and down, and you don't really control that very much. And also, containers use the health check much more rigorously. Kubernetes will actually go and probe the health check every however long you define, and it will use the readiness check to make sure that the container is ready before it spins up anything that depends on it. And so you need to actually consider, for example, how do you define ready? In our cases, a container is ready when it's actually connected to all the databases and made sure it can connect to Kafka and make sure it can see Elasticsearch. If none of these things, if one of these things doesn't happen, the container isn't ready, and so spinning up any dependencies makes no sense, because they would also not be ready. They would just all fail, because their health check defines being able to access the first service. Sorry, I meant to do this. All right. So that's a small thing I wanted to touch on before I move on. The whole point, really, of using containers is so you can manage resources more granularly, right? It's great isolation. There's a bunch of other benefits, obviously. You can spin up identical environments. It helps QA and testing. But when we talk about production, running stuff in production, the thing I really most care about as the architect for this product is I want to be able to cram as much workload into as few VMs as possible to reduce costs, to increase isolation, and to make it easier to manage all this stuff centrally, right? And so the main thing to do that is to be able to manage resources, right? And one of the things all the container orchestrators allow you is to over-provision resources, right? You can go and you say, if you don't actually specify any limits, by default, Docker will let the container do whatever it wants. It will allocate as much memory as there is on the host, and it will be able to use as many CPUs as there are on the host, right? If you don't actually give it hard limits to resources. Same with block I/O, by the way. There's no way to limit network I/O yet, as far as I know. And so it's strongly recommended to at least define the upper limits. You might not define the initial resources. You can say, OK, well, use whatever you want, but go only up until a certain amount. You don't actually, when we started playing with this, one of the things that we got wrong is we didn't set any limits, and so it was pretty much effectively the same as running a bunch of services all on the same VM. They still interfered with each other. They still created burst usage of CPU, which affected other services. It wasn't actually, we weren't reaping the benefits of using containers. And so we went around and we actually defined what makes sense in terms of resources for every class of service. And once we did that, we had the minimum resources and the maximum resources that you can get. And then it became much easier because we could actually calculate, OK, this VM, this size of VM on Amazon, can run up to X number of certain service. It made it much easier to actually provision services and rely on resources being available when you spin up new services or scale up and down. Right. Also, most Docker, Swarm, and Kubernetes let you specify autoscaling. It's much more powerful in Kubernetes. You can create very complex rules for when to scale. Unfortunately, they all pretty much rely on criteria like CPU. Our services, except for 2 small services, are not CPU bound. They're usually either I/O bound, and they read from Kafka, and that's what defines how fast they work, or they're network bound because they do outside network requests. And so we can't really use autoscaling to scale them because they might be using 0 CPU and still be overloaded because they're waiting for 1 million requests to return. Right? And so we're having to evaluate this and actually create external tools to detect what constitutes load for a container and when to scale it externally, because we can't really rely on CPU-based metrics to scale the container. Right? This is where it helps to have external metrics like we were talking about earlier, because then we can probe the metrics, see how, for example, how many requests each container serves, and if it's above a certain threshold, you scale out the service, you spin up new containers of the same type. Right? And so the whole point was it's dangerous to over-provision, and you need to actually consider whether it makes sense to pin certain containers to certain machines. This actually brings us to managing state, right? And I'm not sure what time it is. Oh, we're good. So managing state is, there's two things. One, there are no stateless applications, right? I mean, as soon as you allocate memory, you have state in your application. Yes, there are very stateful applications and less stateful applications, but all applications have state. And usually, it's not a good thing to lose the state because the container went down and came up in a different machine, right? So even if you're doing things like, for example, how many people use Kafka or Kinesis or something similar to read messages? It's like 5. Oh, you guys disappoint me very much. Is everyone just doing microservices? Who's doing microservices with REST? What are the rest of you doing? All right, fair enough. But OK, imagine you have a REST service, right, and it gets a REST request. Now, sure, the service is stateless. It will go to a database. But while it's handling, presumably not just a single request, but a bunch of requests coming in all at once, all of these requests are state in memory. If the container suddenly just goes down, you will have lost however much work you were doing at that moment, right? Sure, you can build reliable services, and the service that called them will try it again. All that stuff is true. But the fact remains, you lost some state. You have to handle all that stuff. And this happens with VMs as well. But as I said, VMs don't actually restart all that often. That's not a normal occurrence. Containers do restart very, very often, right? And they give you a certain grace period to shut down cleanly, but you can't just stop services cleanly every time. And so this is something you have to consider, because when you build this application, when you're building this cloud-native application, which is a silly buzzword, but the point is you have to consider that your application is very impermanent and do as little work in state as possible. Unfortunately, there are some applications which are the very definition of stateful, right? Databases, obviously. There's really nowhere, you can only roll statelessness so much until you can actually have to store the state somewhere. So it goes into a database or Kafka or whatever. And then the question becomes, do you run your databases or data stores on containers, right? And the answer is yes, up to a certain point. If it's a single node database, let's say you're running a MySQL or any kind of SQL flavor, which is a single node, not clustered, or you're running a one Mongo node or whatever it is, it makes perfect sense to do that. There's no issue with it. Every orchestrator allows you to pin a container to a specific machine. So for example, you can define that this particular host only hosts containers tagged with database. And you only have one container tagged database in your system. So this whole machine belongs to this one container where SQL Server lives. Okay? And that's perfectly fine. It doesn't actually give you any isolation benefits, but you can manage your database with the same tools you manage all the rest of your system, and it makes sense. As soon as you go to cluster data stores, right? So your Kafkas, your Elasticsearch, Mongo, Couchbase, whatever database you have, that's actually clustered, and there is significant cost to losing a node and bringing a node back up, it pretty much stops making sense to deploy those on containers. Because above a certain point, for example, our main Elasticsearch cluster has 15 terabytes of data in it. Right? It's 32 nodes with 15 terabytes of data replicated once. And so if we lose a node, then that means we need to bring a node in and then replicate something like half a terabyte of data from all the other nodes to that node. If that happens more than once every week or so, we're going to have serious issues, both in the platform, in the DevOps. It's not a painless operation. And this Elasticsearch, where it's read-only, right? We're not actually using it to store that much data. We mostly retrieve it from it. If it's Kafka, restoring a Kafka node is a very painful operation. It can actually break things. So far, we've strongly avoided putting any kind of stateful data stores on containers. I personally wouldn't feel comfortable doing that anytime soon until we actually get better tools to handling state. Kubernetes are moving in that direction. There's a thing called Stateful Sets, which let you create containers with identity, which is kind of an oxymoron. The whole point of containers is that they have no identity. They're whatever. But Stateful Sets lets you create a container that has an identity. It keeps the same IP, even if it goes down and comes back up somewhere else. Keeps the same IP, keeps the same container ID, which is important. A lot of clustered systems use the IP and the host name as the identifier for the node. So, for example, Couchbase, I worked at Couchbase a while ago. If a node goes down and comes back up with a different node name, it will not be able to rejoin the cluster. The cluster will reject it because it will think it's a new node, right? So in a stateful set, it will go down, There's going to be some downtime, obviously, for some of the data, but it will come back up and be able to rejoin the cluster because it's the same, but not really, node. Right? So Kubernetes is moving in that direction. We still don't really feel comfortable using this for our 15 terabytes of data because it's just too expensive to move terabytes of data around. At some point, it will probably be OK. I'm not sure when it's going to be. I would guesstimate probably a year from now at least. Right? So last thing before we finish, because we're coming up on time, there's a few things you need to consider. This is mostly more DevOps-related things, but you need to define the behavior of restarts and updates. Right? What does it mean for you to update an application? Sure, in your case, right, you build a new Docker image, you update, you commit that to GitHub, you do Docker build or whatever, and you have a new version of a container. But then deploying that container might not be as easy as, OK, we'll just update every container in turn. Right? Because what if, in a lot of cases, having two different versions of the same container running side by side is a bad idea, right? Because one has one schema and the other has another schema. And now we have to do a bunch of work on the dev side to handle two schemas at the same time, right? Do different versions of objects that you're going to be storing and reading, right? And so it's not as easy as just saying, OK, well, when you're doing rolling updates in the deployment file, update containers 2 by 2 or 1 by 1 with 10 seconds difference between them. That means that you have 10 containers with 10 seconds in between. There's 100 seconds where you have a mix of versions in your application, and you can't be sure which version is working at any given time. And so this is something that you don't really have a good answer built into any of the orchestrators right now. You actually have to manually, for example, create a new service and switch the load balancer to it. So you have a new version working all at once. Or you have to do a lot of work and make sure that your containers, your services, are fully backwards compatible. So if they get an old version of an object, they can actually handle it, or the new version of an object. So they have to be both backward and forward compatible if you want to do rolling updates. All right? So we have like 30 seconds for questions. And should just one really quick question? All right. No one volunteers. That's fine. We're going to end 30 seconds early. And if you have any questions, I'll be here. I'm happy to answer. Otherwise, thank you very much for coming. It's very late. Let's go to the party.